who is always awareness program against the climate change to awareness program for the climate correction. He's also an unpaid leave in IIT Bombay professor. So he also is a solar ambassador in India. So according to the Government of India Ministry of Power, there are various various fossil fuels utilized to produce in the electricity. There are the major, we can see this chart, like coal and lignite and gas, diesel, hydro and nuclear others. There are major contribution coal only in producing the electricity. So we know about that non-renewable energy resource, like again to emitting the various gases to increase one of the major contribution to the climate change. And the renewable energy source like various hydro and solar and hydropower, there is no harmful emission and naturally it's abundant resource. So apart from this, the solar energy, it is immense potential to produce the electricity, and also there is no harmful emission and waste. That is also its requirement of next generation electricity production. So that solar energy utilizes the devices called solar cell. This device is working. So principle of photovoltaic effect, we know about in physics is photovoltaic effect. Like light energy is directly converted to the electrical energy. We can see the simple PN junction solar cell. It's after eliminating the light on the solar surface that the charge separation takes place, like electron towards the N-type semiconductor and holes towards the P-type semiconductor, so they're producing the electricity. That solar cell, it's classified mainly to three major generation. The first generation solar cell is made up of crystalline silicon and single crystalline, one of the leading technology in the photovoltaic industry, and also is the higher power conversion efficiency. And second generation solar cell entirely based on the silicon and thin film solar cell, like cadmium telluride and cesium cadmium indium arsenide based CIGS. And third, this solar cell generation, it is mostly utilized in the thin film based technology. However, after the third generation dye-sensitive solar cell and organic and perovskite solar cell is now the researcher working on this perovskite solar cell, because of the now getting the more than 30% efficiency, like now the Indian researcher in IIT Kanpur recently reached the 30% efficiency in India. So the perovskite solar cells also after booming this technology. Even though compared to the first and second generation solar cell, this dye-sensitive solar cell, why it is become more important? Because one of the major things is lightweight, and also it easy manufacturing and easily handling, because of when we are using the silicon based solar cell, we need for the handling is more handling process and is very precise, because when we are keeping in the outside of this solar cell, it is making when we it's dust particle on the surface, it is again it's a problem. The getting efficiency, it is reducing day by day. So and also when we keeping in the silicon solar cell in outside, it's only sunny days only we can utilize the to produce the electricity. Apart from this, gloomy day, particularly in India, it's sunny days and it's partially. So mainly depends upon the intensity and angle of incident. But disensory solar cell we can use in indoor application also, because of this is not depends on the light intensity as well as angle of incidence. So again, apart from this, disensory solar cell have the various advantages like lightweight and transparency. So we can use in Windows application and to produce the power in dim light also. We can use in that indoor for the in room. And low light conditions, because of the electricity it is producing in the low light condition also. Apart from this, the cost of the solar cell per watt also the more cheaper than first and second generation. We can see this. So this is the working principle of disensory solar cell. We can see after elimination of light on the dye molecule, the photoexcitation it takes place. The electron it is excited to the highly occupied molecular orbital to low unoccupied molecular orbital. That electron it is frequently injected to the semiconductor based material to reach the external circuit. Then this dye molecule get regeneration, getting one electron from the iodide-triiodide redox couple. Then this iodide molecule getting electron from the outer circuit. This loops is continuously to produce the electricity without any mechanical force. Yeah, the photoanode it is made up of the semiconductor material. It's monolayer of dye molecule on this. And electrolyte it is composed of iodide and triiodide couple. And counter electrode it is always utilizes the platinum based counter electrode. Even there is a advantage in the disensory solar cell have some major issues like in both photoanode and counter electrode part, because after eliminating photo excitation, the electron not only possible to reach the external circuit and also to recombine towards the dye molecule and also the electrolyte. This recombination reaction to reduce the overall performance of the devices. But we know the charge injection and recombination is thermally equilibrium, and while the people are working is for the highly conducting layer to increase the charge injection efficiency, and as well as they're modifying the structure to the core cell, like a core cell nano structure to reduce the to increase the energy barrier to reduce the recombination reaction. And second things, the platinum is highly cost. We know about the platinum is a highly cost and also noble material. And a prolonged time, this platinum contact with the electrolyte, it also possible to corrosion and reduce the to produce the harmful gases. That is also, it is a negative impact in the devices. So the people are working in both sides, anode and cathode, like a photoanode and counter electrode. to overcome to efficient charge transport layer to minimize the recombination loss, and also we say that ultra fast electron injection to improve the electron injection efficiency. Also we can reduce the recombination reaction. So apart from this, the transition metal chalcogenide, it is a highly electrocatalytic activity, and this composition that the transition metal like nickel and cobalt, like molybdenum, is composite with composition with the chalcogenide, the various chalcogenide material like oxygen, sulfur, like selenium, to improve the electrocatalytic activity. And also, when we are tuning this chalcogenide concentration, we can achieve the higher electrocatalytic activity. That is also improve the overall performance of the disensory solar cell. So based on this, we have designed the cobalt sulfide and RGO hybrid composite counter-electrode to alternative for the utilized in the counter-electrode DSSC application. From the basic characterization, from the XRD, we can see that plane of 11 and 200 and 210 corresponding to the cataract structure of cobalt sulfide. After inclusion of graphene oxide, there is no changing in the XRD spectrum. Basically, I didn't mention in here the preparation technique because of time consuming. Like here, all the preparation technique using in the hydrothermal method. So after inclusion of graphene oxide, it is entirely reducing. We didn't detect the characteristic peak of the GO due to the cobalt sulfide and RGO interaction. It is very high. And apart from this, here we can see in the Raman spectra, one of the clear idea to how the vibration modes presence in this. We can conclude the composition as well as how the vibration modes its presence in this composite material. We can see this cobalt sulfide material along with the cobalt sulfide RGO nanocomposite. We can get along with the characterization vibration modes of cobalt sulfide. There is two bands are present, like 1350 centimeter inverse one and 1550 inverse centimeter inverse due to the D and G band. The D band, we know after preparation of preparation of graphene oxide, because of everyone using modified Hammer method, there is a hydroxyl and carboxyl functional group attached in the both sides. So the defect, disorder and defect structure in this indicate the D band. At the G band, it is highly due to the in-plane vibration of carbon atoms. So we can see the scanning electron microscopics. The pristine cobalt sulfide, it is like a spherical-like structure, and after inclusion of RGO, there is the cobalt sulfide particle highly attached in this thin graphene oxide sheet. So here, the graphene oxide sheet, it is restacking of graphene oxide sheet. It is highly reducing because of this particle. It is acting like a binder. So after the transmission electron microscope, we can see the thin layer, the cobalt sulfide particle. It is covered over the thin layer of graphene oxide sheet. Here we have confirmed the cobalt sulfide nanoparticle is attached in the reduced graphene oxide sheets. From the electrochemical and photovoltaic characterization, we can see the cyclic voltammetry text, one of the studies to how the counter electrode react with the electrolyte in the component of iodide and triiodide electrolyte iodide and triiodide couples. We can see that after potential sweep, like minus 0.6 volt to 1.4 volt, there is a both anodic and cathodic peak presence in the both side, all the sample. Normally, this cyclic voltammetric test we can get from this 3 electrode system, like platinum as the reference electrode, and silver and silver chloride as a reference electrode, and working electrode as if we have prepared the material, prepared sample is coated on the FTO substrate. This the higher current densities indicate how the electrolyte content in the iodide couple, it is reducing in that counter electrode. So it is showing the higher electrocatalytic activities. So after that we can see the cobalt sulfide, there is a lower current density. After inclusion of reduced graphene oxide, the charge current density is increasing because the RGO is providing more active sites to interact with the electrolyte to improving the charge current density. And also the redox potential, it is a major concern in this DSSE application because there is a fast dye regeneration. It happens to reduce how much fast the electrolyte it is getting reduced in this counter electrode, then only to fast dye regeneration to improve the overall performance. Then this different scan rate, how the oxidation and reduction potential is changing. Here we can see the linear relationship with the for increasing the scan rate. After charge electrochemical impedance spectra, normally the Nexus plot it is showing, it is indicating the semicircle that it is charge transfer resistance, how it is a different interfacial process in this DSSE. So electrolyte and electrode and like photoanode and counter electrode interface. It is how the charge transfer resistance in these devices. So moreover, here after inclusion of cobalt sulfide in RGO, that is increasing the electrocatalytic activities, and also the semicircle of arc, it is implies the charge transfer resistance. Here we can see that the seat resistance of the cobalt sulfide after inclusion of RGO, it is reducing. It is indicate the high electron transfer, high electron transportation. So after current and voltage characterization, this is a reference from this platinum-based DSSE device. And moreover, the cobalt sulfide, we can see the even though the current density it is a 10, short circuit current density it is a 10, but in the shunt resistance it is increasing. The shunt resistance it is normally due to the a lower shunt resistance, it is indicating that higher leakage path. But in this case, it is after inclusion of RGO, there is increasing the higher shunt resistance. Because of that, RGO it is providing the higher electrical conductivity. So this is also implies that higher charge, higher current density from the CV plot, and there is a charge transfer resistance also. It is decreasing in the from the over the frequency region. So as implies that the CSG2 sample, it is indicate the maximum power conversion efficiency of 5.46. So the after inclusion of RGO, that is also negatively impact in this fill factor. We can see here CSG C3 sample, that is decreasing the fill factor due to the higher charge transport resistance. So the second, we have also tried a ternary nano composite, like a nickel cobalt oxide and RGO and PANI-based material, ternary composite material, how it is inducing the electrochemical behavior as well as the photovoltaic performance. So in this basic characterization, we can see the blue color is the graphene oxide peak. Like after hydrothermally, the peak it is shifted to the higher angle because of that is reducing the carboxyl and hydroxyl group from this in the GO. So the same analysis, we can see that the nickel cobalt oxide, it is a sphere-like structure, and after composition with the in situ polymerization of PANI, there is no changing in this structure. There is not that much changing in this structure, but because of that cobalt sulfide particle, it is inclusion in this in between the PANI and reduced graphene oxide sheet. So same this. From the CV analysis, we can get the higher charge current density, and apart from this higher current density and reduction peak, because of this EPPP value, it is this EPP value, peak to peak separation from anode to cathode. This how the fastly the counter electrode it is interact with the electrolyte to this is a fast charge transfer kinetics. It is helpful for the counter electrode application. As we this is also basic characterization Raman spectra from GO. It is getting D and G band, and after inclusion of RGO, there is a more peak, along with the nickel cobalt oxide peak, there is also the D and G band. It is present in this composite. So we have confirmed the nickel cobalt oxide and RGO PANI in this composition. From the electrochemical impedance spectra, we can check that over the frequency region, for higher frequency to lower frequency, there is two semicircle it is showing. The first semicircle, it is indicate the charge transfer resistance from the electrolyte and electrode, like the counter electrode to electrolyte. So after inclusion of the ternary composite, there is decreasing the charge transfer resistance from, we can see the red color figure. It is showing that it is the radius of the not the charge transfer resistance is decreasing. We get the improving the charge transportation. From the IV curve, we can see that the short circuit current density and open circuit voltage. Here, short circuit current density is depends upon the how the light harvesting efficiency takes place. Here, after this is the platinum-based reference electrode, getting the high fill factor. We can see the nickel cobalt RGO composition is slight decreasing in the open circuit voltage. Normally, the VOC it depends upon the Fermi level of semiconductor material like TiO2 and potential difference between the electrolyte. So it is slightly reducing the fill factor compared to the platinum, but in the charge current density, the short circuit current density, it is increasing because of the ternary composition. It is the RGO, it is providing the more active sites to participate the iodide and triiodide couple to increase the more number of electrolyte to reducing. So that's why that higher dye regeneration happens. So the current density it is increasing. So overall, the nickel cobalt RGO composite with in situ polymerization, it is increasing the overall maximum power conversion efficiency of the 4.2. Also, we have tried to check that how the device is working in the several times, like 600 minutes on and off condition. There is no changing in the current density value. We can see the same same current density value. It is directly implies the how stability of in the devices. So the same, it's initially we have tried that iron, cobalt pyrites and RGO composite. And second, we have also tried to how the transition, especially in the pyrite material, it is behavior in the counter electrode. We have checked in that in the graphene oxide composition. In this, I didn't show in that basic exotic characterization. Here with SEM analysis, we can see that the particle getting it is more agglomeration in the FeS2, but after inclusion of RGO, there is agglomeration of particle, it is highly reduced because of the graphene oxide. It is good platform to growth on the FeS2 nanoparticle. So that's the particle structure also it is changing while increasing the concentration of RGO because of this more growth of the FeS2 on this graphene oxide sheet. So, and also we can see that in TEM analysis that iron pyrite hexagonal like structure, it is growth on the reduced graphene oxide sheet. And also same like oxidation and reduction peak, like its presence in all the sample, which indicate this material it is interact and also producing the high electrocatalytic activities. One of the things, apart from this low PPP value and also the higher current density, from the peak potential, it is peak potential shift towards the negative. So because of how the electrolyte it is low over potential to reducing the electrolyte, it is this is also it is indicate the how charge transfer kinetics it is increasing, inclusion of graphene oxide. So reduced graphene oxide, it is not only providing the more active sites to enhance the electrocatalytic activity, and also providing the increasing the electrical conductivity. That's why we have seen this reduction peak. It is more lower potential. This is also helpful to increase the fast regeneration in the DSSE. And this is also same thing. It's like how the linearly increasing linearship relationship with the various scan rate, that FeS to G2 sample, it is increasing oxidation and reduction potential. As we know that oxidation, it's back to the iodide to triiodide, but reduction peak, it is how the iodide it is get back to the triiodide molecule to donate the one electron to the di molecule, getting high di regeneration. And this is a tuple polarization curve, also one of the technique to how the charge limiting current density it's happen. How limiting current density is increasing while inclusion of RGO, there is this slope, it is indicate that it is maximum limiting the lower limiting current density to improve the electrocatalytic activity. And also we can see that the radius of the semicircle, as we already told that the radius of the semicircle, it is indicating the charge transfer resistance from the electrode to electrolyte. After inclusion of RGO, there is charge transfer resistance, it is decreasing because of RGO, because of the high electrical conductivities in this RGO composite. And yeah, this is a cyclic voltammetric parameter. We can see the FeS2G2 sample. It's a high current acceleration current density as well as the high reduction current density. It is indicate that high electrocatalytic towards the iodine and triiodide. And also the lower redox potential, how the fast driving force to electron, how driving force to reduce the electrolyte to improve the electrocatalytic activity. And we can see that FeS2G2 sample getting more power, FeS2G2, it is getting more fill factor compared to the FeS2 because of the FeS2 given the electrical FeS2 and FeS2G2, there is no changing in the short circuit current density, and however we can see the open circuit voltage, it is highly increasing. That is also, it is indicate the reducing the electron recombination. Apart from this, we have also tried how the topological material utilized in this counter electrode pod. Normally, the bismuth telluride material, nobody can used in this Dyson ray solar cell application because of is already established in the thermoelectric material. But one of the thing I have captured in this bismuth telluride because of this, and how the both surface and bulk and surface states. While this material, it is highly conducting in the surface state, but insulating in this interior. So the electron can move freely in this 2D surface because of the highly spin orbit coupling. That's why I have interested to do in this work, in this topological material, how the behavior in that reduce the electrolyte in the counter electrode application. This is the basic XRD spectrum and fundamental analysis. After inclusion of SWCNT, there is no changing in the peak position, but peak broadening it happens in this bismuth telluride SWCNT composite. It is indicating that CNT it is attached in this CNT in this composition. And also we can see the Raman spectra along with the characteristics vibration modes of bismuth telluride. There is a D and G band and 2D band is present. It's indicating also the CNT, it is inclusion in this composition. And the pristine bismuth telluride, it is spear-like structure. After hydrothermal condition, there is the spear-like structure. It is affected in this growth condition, but the sheets are more attached in this CNT composition. We can see in this CNT along with bismuth telluride sheets on growth on that attached in the CNT, functionalized CNT. So this is providing the more active sites to improve the electrocatalytic activities. We can see further in this electrochemical behavior. Yeah. This work also is recently published in this Journal of Colloidal Interface, and the same. The CV analyzes it showing both anodic and cathodic peak presence in all the three sample. We can see not only increasing the current density, and also the peak-to-peak separation it is reducing, highly indicating that how fast given the fast driving force to reduce the electrolyte. And sorry, I didn't change this spectrum because of this is the bismuth telluride. After inclusion of SWCNT, there is charge transfer resistance. It is reducing. In the blue color curve, it is showing that the charge transfer resistance, it is highly reducing, and also the seat resistance of the electrode also reducing after inclusion of the CNT, as indicating that there is no changing in the short circuit current density as well as the open circuit voltage. The short circuit current density indicating the how light harvesting, there is no changing in the, because of all the electrode, all the devices we are using in the TiO2 only the photoanode material. But in the case this the light conversion, light harvesting efficiency does not change, but only the fill factor of the material it is changing. We can see this how the charge transfer resistance is reducing, and this is the. Actually, it's the blue color curve. I changed this. It is wrongly mentioned. This is the blue. This is the bismuth telluride CNT composition. Yeah. So fill factor, it is one of the major things. How electrical conductivity and how the charge transport resistance, it is all depends to improve the fill factor value. So the fill factor only it is tuning. So I didn't show I have changed the 3 composition, but linearly increasing the fill factor value. But I have shown only for the one sample. So the bismuth telluride and stably CNT composition, it is getting still less power conversion efficiency compared to the platinum, but to improve the, first time we have checked this how the bismuth some topological surface state it is induced in this counter electrode application. And also this is I'm not going to discuss because of this already in this is that same material I have checked with the photodetector performance. And as well as is a counter electrode sites have some major issues. So we have utilized in the carbon-based composite material how the electrical conductivity is increasing and providing the more active sites to interact the electrolyte. Apart from this, the photoanode side also we have worked. So in this one is the first work in this TiO2 ZNO core cell structure. This is the basic characterization. There is a TiO2 ZNO. Normally, the TiO2 is TiO2 and zinc oxide is a more wide band gap material, but the zinc oxide is a slightly higher band gap compared to the TiO2. So, after injection of the electron dye to semiconductor material, but back electron transfer is highly reducing, which indicating that we can see the short circuit current density, it is slightly increasing when inclusion of ZNO, which indicating the once injected to the electron in this semiconductor material, here the ZNO, it is acting like an energy barrier. So the back electron transfer reaction, it is highly inhibition. So that's why the short circuit current density it is increasing. So that's why it is getting maximum efficiency of 3.25. And in these devices, all the platinum in these devices, there is no changing in the open circuit voltage, because I've already told the open circuit voltage, it is depends only the material and potential difference between the electrolyte and the semiconductor layer. There is no changing in the open circuit voltage. And also, we are trying to reduce the graphene oxide not only in the counter electrode side, and also we have tried in the photoanode side, because the TiO2 it is have the multiple grain boundaries. So the charge transportation, it is a zigzag manner. It is possible to increase the internal resistance in this material. So that's why the RGO also we have utilized in this photoanode side also. We can see this is the basic characterization, GO and reduced graphene oxide, and TiO2 composition getting D and G band. And here we can see the we have checked the impedance in this over the frequency region. Initially is over the frequency, first higher frequency to lower frequency region. How we can get the semicircle, the middle semicircle. Initially, the counter electrode part, it is charge transfer resistance in the first semicircle, but in the middle semicircle indicate the transfer resistance in the and it's a dimolecule, the semiconductor material to electrolyte. But in this counter electrode part, we have worked in this electrode and electrolyte, means counter electrode and electrolyte. Here the semicircle, it is reducing after inclusion of the RGO, so improve the charge transportation. So the RGO, it is not only providing the getting more dimolecule absorption on the surface, and also it is improving the charge transport resistance. This is the Bode plot. The Bode plot, it is we can get the time constant, how the electron it is accumulated in the conduction band. That is time also, it is important, because of that time it is a more time stable, the electron is stable in the conduction band. It is also possible to the charge injection efficiency. So we can get the optimized reduced graphene oxide seed. We can get the maximum power conversion efficiency of 8.62. This is all the work in this published in the reputed journal, in the Journal of Allieds and Compounds. And also, both initially, first trial we have checked how energy barrier to product the back electron transfer. This The second work, how reduced graphene oxide improve the charge transportation in these devices. And the third one, also we have tried the how surface plasmonic effect in inducing the light harvesting efficiency. As we know that surface plasmon, there is no such a role in this for improving the light, the charge transport resistance, but the higher charge hot carrier, we can improve the what I'm telling you, like accelerate the charge carrier from the conduction band. So that it happens to the power conversion efficiency, it is slightly improved only in this for the short circuit current density, because of the when AG, the silver nanoparticle on the ZNO, there is acceleration in the conduction band of the ZNO. So that's why we can get the light harvesting efficiency to improve the only showing that in the short circuit current density. There is no such a changing in the open circuit voltage. This is how we have fabricated the solar cell in the lab scale as well as the and large scale submodule. We can make the TiO2 paste and grinding and screen printed. Here we have optimized the TiO2 photo anode. It's screen printing method like 14 strokes. Here 14 stroke over the layer we have coated. It is getting the optimum thickness of 14 micrometer. We're getting the like this this is the 14 micrometers thickness, and after dye absorption, it is showing like the more dye molecule it is absorption on this surface of the TiO2. And this is the counter electrode also. We have tried in this manner, like a screen printing method to coated the composite electrode. And this is the large scale strip, single strip on this single electrode, single FTO transparent conducting substrate. Here we can see that we have tried the two strips, separated strip on this FTO substrate. We have etched and also we connected together as a one photo anode. So we have this is devices making in the binder clip, and this is the devices testing, and we can get we have tried this the three sub module. We connected parallel and series. After illumination, there is a glowing the low LED power of low power consumption devices. Here, this one is seriously connected this three submodule, and we are getting that maximum 2.94 milliampere current and voltage 2.1. This 2.1 volt, it is consumption of the red and also the green power, green color LED. This is the corresponding IV curve we have get in this electrochemical workstation. Yeah, summary. And the counter electrode part, the transition metal chalcogenate when composite with the reduced graphene oxide, it is not only providing the electrical conductivity and also providing the higher active sites to more number of electrolyte. It is contact with the counter electrode to improve the electrical conductivity and also the electrocatalytic activities. And bismuth telluride based material, first time we have tried. We are getting the maximum conversion efficiency, still low, but we are tried in various carbon composite material. It's ongoing work to improve how the topological material it is working in this counter electrode, especially in the DSSC application. And And photo anode side we have used in the TiO2 ZNO coarser nanostructure and TiO2 RGO nanostructure and AG nanostructure. We are getting the we are getting TiO2 ZNO. The charge separation it is increasing due to the ZNO acting like an energy barrier to improve the charge injection efficiency. And TiO2 RGO nanocomposite nanostructure, we are getting improve the charge transportation. The RGO is providing the more electron transport channel to improve the power conversion efficiency. And the silver nanoparticle, it is accelerated the conduction band of the ZNO to improve the light harvesting efficiency. That is also leading the solar power conversion efficiency. Yeah, this is my university and Department of Physics in this University of D Atacama. And yeah, this South America continent, the Chile is located from this here. How the nearby this country we well known for the Chile only for the football match. It's and nearby countries Argentina like Brazil all are. It is like most sports oriented and their country that only we know. Apart from this, there is lots of places is there, and I need to show these things because of there is lots of things it's there in visiting place like Moon Valley. We can feel while we are touching in the surface, we can see the we can feel like a moon. We can see the picture also, and the Grand Santiago Tower, one of the it is not a Burj Khalifa in the world tallest building, but this one is the I think 10th tallest building in the world. And also the Andes Mountain is located from the west coastal of Chile, and this is the world's longest mountain, means continually connected to mountain in this and this mountain. And the world very dangerous active volcano is located also in the Santiago, in the Atacama region. I'm also, I think, away from the 800 kilometer from University of Atacama. It is there. This is also one of the dangerous volcano located in the. It's still active in this most dangerous in the world. And thank you for your patience. And also, there is lots of opportunities there from in outside the country. We have we always searching in anywhere. How the outside opportunity is there. So we are a young research student, so who we need any help to getting or know any doubt from this, how we can approach the outside country, getting any fellowship, kind of postdoctoral fellowship or PhD, and you can contact me, and I will show the way how we can approach the professor and how getting the fellowship. This is also one of the Fondesit fellowship only I got for the 2023. So you have any doubt or you have any queries related apart from this this section also, you can feel free contact me. Thank you.
Thank you, sir. Now we'll have query session where you can ask any questions. Thank you so much, Mr. Manigandan, for sharing your valuable insights with us. Now we would like to invite everyone for a quick photo session with our esteemed speaker. Photo session will be held after tea break. Now we'll have a short tea break where you can also take some time to refresh and assemble here by 11 o'clock.